Warahmatullahi wabarakatuh, and a very good day to all students. Um, okay, the topic of today's lecture is still on energy loss determination. So before we start, it's good to reflect why it is so important to learn about energy loss. Okay, energy loss is something that we cannot avoid. So that's why we have to learn, because in your design, if you want to design an irrigation system, you must include energy loss term in your design. Okay, why? Okay, maybe we can imagine if you want to have this kind of irrigation system. So in an efficient irrigation system, you must have a uniform flow rate, because you want your plants, you want your crops to have equal amount of water, because you want to have uniform growth for all your crops, right? So if we do not include energy loss in our design, so there is a very high probability that your plants will not get enough water, or uniform water, right? So I hope you can understand this. Okay, so energy loss, as we learned before, because now we are dealing with major energy losses. So you have learned earlier that the energy loss can be determined using Darcy-Weisbach equation for turbulent flow, or it can be determined using Hazen-Williams equation if the flow is laminar flow. Okay, so you already know how to determine the types of flow using Reynolds number. Okay. So maybe it's very helpful if you can understand this energy equation. Previously you learned about these energy lines, but without the energy loss. Now we want to see if we have this energy loss, how the energy line looks like. Okay. So first of all, imagine that you have point 1 and point 2 in this figure. So the water the water move from this point to this point. So at this situation, the potential energy for point 1 is lower than the potential energy at point 2. Okay, but the pressure energy at point 2 here is lower than the potential energy at point 1. Okay, since the pipe is of similar size, so we will have same V. Yeah, because Q is equals to AV. So when you have similar A, so we'll have similar Q. And in this case, since you have same V, so the line will be the same height. Okay. Okay, so what will happen here is that you add energy loss here, because you know that from point 1 to point 2 there will be energy loss. So that's why the energy here is higher than this at point 2. So this is how we visualize the head loss according to this energy line. Okay, so from this figure, okay, the term head loss for HL is also used for major and minor losses in pipes. Okay, so the head loss, it is called head loss because you can observe apparent reduction of height from this energy line. Okay. Okay. Well, in this figure, it's very busy. I understand. First, follow my pointer. Okay. So you go to this part first, Darcy-Weisbach or Moody diagram. Okay. So first of all, when we deal with energy loss, so we have to determine sometimes D, the diameter of the pipe, and we also sometimes want to find Q, and we also want to find head loss, right? And sometimes one of these information is missing. For example, okay, if we are using Moody diagram, so normally D and Q is given. So we can easily find HL, energy loss. Yeah. So we can use Darcy-Weisbach or Moody diagram. Okay. But then sometimes Q and HL, we know, but then we do not know D. Okay, so if we do not know D, how can we find the Q, right? Because Q is equals to AV. Okay, so in this case, Lee, okay, this engineer called Wen Huixing Lee, he's Yung Lee, okay, he developed his version of his diagram according to Moody, so he called it modified Moody diagram, Lee's pipe flow diagram. Okay, so this diagram is suitable when you have Q and you have HL, but you do not know D. So it will be easy for you to find D when you have Lee's diagram. Okay, in the third situation, okay, this engineer, Casey Asthana, he combined Darcy Weisbach and Moody diagram, so he comes out with his own diagram, which he called as Casey Asthana's diagram. Okay, when can we use this diagram? So when HL, energy loss, and diameter are known, but you want to find Q, so it's easy for you if you can use this diagram. Okay? Okay. Okay, these are the scientific methods for determining H loss. But we also have the empirical methods. The empirical methods is mainly from experiment. So, yeah, for example, this Hazen-Williams equation is derived from experimental data. So, from his experiment, he proposed this relationship, which is V, average velocity, is equals to 0.85 times Hazen-Williams coefficient, and times R. R is hydraulic radius of flow, and also S. S is ratio of HL to L. Okay, and he also proposed his own nomograph. Alright, so there are situations where either Darcy Weisbach and Moody, or either Lee's pipe flow, or either Casey Asthana or Hazen-Williams equation can be used. Okay. Okay, this is a bigger version of Lee's pipe flow diagram, but I think you still cannot see this clearly, right? So I will try to find a better figure for you, and I will share with you. And also this is for Casey Asthana. Okay, this is Hazen-Williams equation. So the Hazen-Williams equation, one of the weaknesses is that this coefficient is not very accurate. Okay. But it is suitable to be used for rough preliminary estimates. Okay, and from the book that I have, according to this book, but it's an old book, this Hazen-Williams equation is used by most engineers. Okay, because Moody diagram is not very practical sometimes, so some of the engineers prefer to use Hazen-Williams equation. Okay. Okay, maybe we can do one example so that you will appreciate the innovation from Lee and also from Asthana. Okay, because in this, okay, let's read the question. In 8-inch cast iron pipe carries water at 40 degrees Fahrenheit from reservoir A and discharge it into reservoir B. The length of the pipe is 500 feet. The elevation of the water surface of A is 3,300 feet and 3,100 feet for B. So you have to calculate the discharge of the pipe. Okay. In this situation, you have to find Q. You want to find Q here. Okay. So first of all, list all information given. So what are the information given? So first HL, energy loss. So you remember just now that I told you H loss is also called heat loss. So in this sense, the difference between point A and point B is considered as H loss. Okay, so the value is 200 feet. Okay, so the diameter is given as 8-inch, length is given as 500 feet, and the material of the pipe is cast iron. So you can refer this to a table and you will get 0.0085. In this case, the question already calculate for us. So the relative roughness is 0.0127. Okay. So now you want to calculate Reynolds number, right? Normally we want to calculate Reynolds number because we want to know the flow type. So once we know the flow type, whether it's turbulent or laminar, then we can move to the next step, right? But in this case, how can you determine Reynolds number because you don't know Q, right? Because in Reynolds number you need to have V, but if you do not know Q, how can you find V, right? So in step 3, we know that HL is given, right? HL is 200. So HL, we can look at Darcy's equation. Maybe we can find V from Darcy's equation. So yes, Darcy equation, we can find V. And we know HL, we know L, we know D, we know 2G. But unfortunately, we do not know F. How can we find F? Because F needs to be found using Moody's diagram, right? But we do not know V, so we cannot know the Reynolds number. How can we find F? Okay, so never mind. First of all, we use these terms first. So you know that V to the power of 2 is equals to 1.72 divided by F. Okay, so leave it like that first. And then we want to find, just now I said that we want to find Reynolds number. So, but we do not know Reynolds number because we don't have V. But we can know the density, we know the diameter, and we know the mu for this situation. So we can always refer density and mu at 40 degree Fahrenheit for water. So the question in this example, so it's calculate the Reynolds number like this. So Reynolds number is equals to 4 times 10 to the power of 4 times V to the power of 2. So in this case, you still cannot solve for V. So we still do not know the Q, right? Okay, so what should we do? Okay, in this case, we have to use trial and error method. Okay, so how do we use trial and error method for solving this problem? So first, you assume F. Okay, so in this case, you have to assume F. So when you assume F, you can find V. Okay, so V you know when you assume F. Okay, and secondly, when you know V, you can plug in V in Reynolds number because you want to find Reynolds number. So V that you get from the first point here, you put into this equation. So you can know RE. So once with the assume F and using the Reynolds number calculated from this step, okay, you can find the F in the Moody diagram because you already know relative roughness, right? So you can find F. So the question is, do you get the same F as you assume? Okay, do you get the same as F as you assume? Okay, if the answer is yes, then you have the right answer. But if the answer is no, then you have to repeat step 1, which means you have to assume new F. Okay, once you assume new F, you have to do these steps again until you get the same F. What I mean is that the assumed F is similar with the calculated F. Then with the F that you refer from the Moody diagram, then you know that you will get the right answer. Okay, so this is an example for you. Please do this example, and if you have any question, please ask me. And you must submit this as attendance for today. Okay, thank you so much, students. Bye.